Hello, viewers. Welcome to class. The topic I'll be treating today is combined probability. Okay, I'm David Max. Now, let's get straight into the lesson. All right. The objectives for today is to understand the definitions of exhaustive and mutually exclusive events using the OR rule. And then we all have the prior knowledge of Venn diagrams, so we shall be seeing how that applies to probability. Now, let's begin. A set of events is exhaustive if the events cover all the possible outcomes. Now, what we mean by that is, now imagine rolling a die. Event A is getting an even number. So this is event A here. Event B is getting an odd number. This is event B here. And event C is getting a factor of 30. This is event C right here. Now let's shade each row to show the outcomes included in that event. Okay. Since we have event A, okay, getting an even number, 2 is even, 4 is even, 6 is even, shaded. Event B is getting an odd number, 1 is odd, 3 is odd, 5 is odd. And event C is getting a factor of 30. 1 is a factor of 30, 2 factor of 30, 3 factor of 30. 4 isn't, so 5 factor of 30, 6 factor of 30. Okay, let's mark that, all correct. Well done, guys, let's move on. Now, are events A and B exhaustive? Remember, exhaustive simply means that the events cover all the possible outcomes. All the possible outcomes here are 1 to 6. 1, 2, 3, 4, 5, 6. So if you take a look at event A and event B and you kind of, check their outcomes, do they complete all the outcomes that we have here? Okay, taking a look at all of these, I think they do. So let's see. Yes, between them, A and B include every outcome from 1 to 6. So events A and B are exhaustive. Let's take the next one. Events A and C, are they exhaustive? A and C, let's see. 1 is filled, 2 filled, okay, 3 filled, 4 filled, 5 and 6. Yes, they are exhaustive as well. You can see that A and C include all the outcomes between them. It doesn't matter that 2 and 6 occur in both, okay? Being exhaustive just means that once you combine the two events together, they cover all the outcomes that are possible. Let's take a look at event B and C and check if they are exhaustive. B and C, 1 is covered, 2 is covered, 3 is covered. Oh, outcome 4 is not covered at all by any of the two events. So I think this is not exhaustive. So the answer is no, the outcome 4 is not included in either event. Now, let's take a quick one. The event relates to rolling a die, okay? Drag each event on the right to 1 on the left, all right, to form 4 pairs of exhaustive events. So what I mean by that is, which of these guys here will you drag and put here side by side to make the event, the outcome exhaustive? Scores, I have scores that is less than 4, that's 1, 2, 3 for this one. Okay, so if I just quickly do this very quickly, for this one I have 1, 2, and 3. All right, 1, 2, and 3. Okay. Let me put it on top here. I'll try to do the same thing for the next one too. I think I'll do it this way. Let's take a look at score is a factor of 12. Score is a factor of 12. Factors of 12, you have 1, you have 2, you have 3, you have 4, and then you have 6. Those are the factors of 12. The next one talks about score is a multiple of 3, quickly. Multiple of 3, you have 3 and you have 6. Okay, you know we are talking about the die, and then on a die, you expect that your numbers cannot be more than 6 on a dice, right here. So the last one is talking about, I'm just listing out the outcomes. Score is a factor of 8. Factor of 8, you have 1, you have 2, you have 4, and that's all. Those are all the factors of 8 you can find on a die. So let's take a look at the ones we have here. Score is more than 2. For score is more than 2, you expect 3, 4, 5, and 6. Score is more than 2. And also, the next one, you have score is more than 4. For score is more than 4, you have 5, you have 6. It's only 5 and 6. Okay, there are more than 4 on a die. Score is less than 6. Less than 6. Less than 6 is definitely all of 1, 2, 3, 4, and 5. All those numbers are less than 6. Okay, next we have score is a factor of 30. Factor of 30, you have 1, you have 2, you have 3, you have 5, and you have 6. Those are the factors of 30 that you have on a die. So you guys take a look at them. Which one completes which one? So you need to quickly take a look at it. Don't mess it up. Now, I have 1, 2, 3, 4, 1, 2, 3, 4, 6 here. This one needs just 5 to be complete. So I can take this and drag it beside it. It doesn't matter if there is an element that, is the same. We just need it to be complete, to be exhaustive. Okay, let me see again. Let me see. I think I'll go for score less than 6 to go with score is a multiple of 3, because 3, 6 is only 6 I need remaining to complete this. So I can take that. For this 1, 2, 3, okay. Okay, I think this goes here and this goes here. Because here 1, 2, 3, there's 3 here, but 4, 5, 6 completes it. There is 1, 2, 3, 4, 5, 4, 6. There's 5 here, so that completes it. This is 3, 6, so this is 1, 2, 3, 4, 5. So to complete it, it's just 6 I need, so 6 is here as well. So I think we're good to go. This is 1, 2, 4, and this is 1, 2, 3, 5, 6. So 4 here completes the outcomes, and then all correct. Well done, guys. So that is how that goes. So remember, exhaustive events, okay? When you put their outcomes together, they must complete the total number of possible outcomes. All right, now let's proceed. We have 2 events. When 2 events are said to be mutually exclusive, okay, that is when there is no overlap between them. Now, when we say no overlap, what we mean is that the outcomes of the first event does not have a common outcome with the second event. Okay, that is what we mean by overlap. All right, here are the events from page 1, and then we added one more, which is a 4th event, getting a 6. We added event D. Okay, now, are events A and B mutually exclusive? Check event A and B. Yes, they're complete. They complete each other, okay? You can see, moving it in, they filled up all the possible outcomes. So it's a yes. B and D, let's take a look at B and D. B and D, if I move that, oh yes, B and D, it's a yes. Because take a look at B, okay? You can see that none of the outcomes are the same. It doesn't matter that outcomes 2 and 4 are not included. Our aim here is to take a look at mutually exclusive, okay? In as much as there is no outcome that is common to the two events, all right, then they are mutually exclusive. Okay, let's proceed. Event A and C. This is A, 2, 4, 6, and this is C, 1, 2, 3, 5, 6. Wow. Okay, do you have anything common? Yes, 2 is common to A and C. 2 is common. 6 is also common. So for that case, the answer is definitely a no. They both include outcomes 2 and 6. So that means you simply say that they are not mutually exclusive. Mutually exclusive two events, okay, that are mutually exclusive must not have a common outcome. Moving on. A dice is rolled. What is the probability of getting either an odd number or a 6? If you quickly take a look at that, odd or a 6. If we take a look at the outcomes that we have for this, we're going to realize that odd numbers, we have 1, we have 3 on the dice, don't forget, we have 5. And then, how many 6 do I have on the die? There's just 1. These are the outcomes. So we see that 1, 3, 5, okay, is talking about 1, 3, 5. Those are your odd numbers, and there's only 1, 6. So how many of them altogether is my required outcome? That is 4. So this should be 4. Probability should be 4 over 6. But of course, we can reduce, and that reduces to 2, okay, over 3. If you mark it, that is correct. The successful outcomes are 1, 3, 5, and 6, and then we're able to do that. Let's move on. Now, let us work out the separate probabilities, okay, very quickly. Let's work out the separate probabilities. Probability of getting an odd number separately, I think odd number 1, 3, 5, so that's just 3 out of 6. And because it's 3 out of 6, we're going to expect that that reduces to 1 over 2. 3 out of 6 is just exactly half. Probability of getting a 6, there is only 1 6 in the die, so that is 1 out of 6. 1 over 6. So obviously, they are both correct. Well done. Now, what do you notice? Okay, and what we can notice here is that the probability of getting an odd number or a 6 is just the sum of the separate probabilities. 1 over 2 plus 1 over 6 will give you 2 over 3. And that was the answer we got before. That's before separating the probabilities. So that tells us that for mutually exclusive events A and B, the probability of A or B can always be written as probability of A and probability of B separately with a plus in between them. So the probability of A or B is probability of A plus the probability of B. Now the symbol for OR is union. And the union symbol, okay, then we can then write the formula this way again. Probability of A union B is probability of A plus probability of B. If you're looking at this formula, guys, you will see that this is taking you back to something related to set theory, talking about Venn diagram. Moving on, guys. The probability of a traffic light being green is 0.5, and the probability of it being amber is 0.1. What is the probability of it being green or amber? So in this case now, we can use our mutually exclusive event formula because we can see the word or. So anytime you see the word or in a probability question, or you see either or, definitely you know you are working with mutually exclusive formula. Please take note of that. Mutually exclusive event formula is what we are going to use. So probability, let's use G and A for amber. We know they are mutually exclusive events. Why? Because the lights are never both on at once. You can't have any of these lights to be on at the same time. It's just one at a time. So there's no way you can have common outcomes. All right? No overlap. Okay? So we have probability of G or A to be probability of G plus probability of A. Probability of G was given as 0.5, probability of A given as 0.1. You add them together, you get 0.6. Very good. Moving on. What difference does it make if the events are not mutually exclusive? Okay, we've talked about mutually exclusive. What if they are not? Okay, how do we know? What difference does it make? A dice is rolled. What is the probability of getting an even number or a factor of 8? Okay, this is the outcomes that we have. The even numbers on the dice, 2, 4, 6, and the factors of 8, 1, 2, 4. What do you observe? I can observe overlaps, overlap 2, overlap 4. So that means 2 and 4 are common outcomes. And that is not what we want for, we don't want that for mutually exclusive. So this is an example of not mutually exclusive events because we have common outcomes from the two events. So take note of that, guys. All right. Now, the successful outcomes are 1, 2, 4, and 6. We're trying to find the probability now. Okay. Without separating yet, if you just think of the events getting an even number and then getting a factor of 8. 1, 2, 4, 6. Because when you look at them together, these are all the successful outcomes for those events. Now, the probability of E or F, since I have 4 of them, that'll be 4 over 6. So the answer is 4 over 6. But let's look at it separately. What happens if we use the OR rule? Now, the OR rule is to solve it separately using the OR rule. The probability of even numbers, E, that's 3 over 6. Factor of 8, 3 over 6 as well. So probability of E plus probability of F, if we had used the OR rule, will be 3 over 6 plus 3 over 6, which is 1. And that is not the same answer when we did it together here. So what do you think happened? The OR rule says these two results should be equal. But what has gone wrong? The two events are not mutually exclusive. Okay? So 2 and 4 are both even numbers and also factors of 8. Those were the common outcomes. So what it means is that you have counted those two outcomes twice. That is what went wrong. So we need to subtract, okay, those two outcomes. And what do? We simply do 1 minus 2 over 6. How did we get this 2 over 6? Because we know we have two outcomes that are common. Okay? So that simply means that the probability of those two outcomes that are common is definitely 2 over 6. When we subtract that from the addition we had before, which is 1, that is definitely 4 over 6, which is the same as the answer we got initially when we did it together. So guys, that has brought us to be able to understand that the probability of even or factor of 8 is now the probability of even plus the probability of factor of 8 minus the probability of both of these. Okay, so we always have to subtract the probability of those common outcomes from this addition. Please take note of that. Very important. That will be the formula for not mutually exclusive events. So there's a difference now, guys. Please take note. There's a difference, big difference. Okay? You don't want to make that mistake, guys, when you are solving any question on probability. This one that I just boxed out, that is what you will use for not mutually exclusive events. If it was mutually exclusive, the subtraction part of this formula, this one, will not be there. It will just be the addition alone here. So take note of the difference, guys. Moving on. So we are now bringing up the formula to let us know that, okay, the symbol for AND is intersection. So in general, this is written as probability of A union B equals to the probability of A plus probability of B minus probability of A intersection B. You guys now remember, I am sure you remember, you have seen this formula before in set theory when we did Venn diagram. You see the relationship between probability and set and Venn diagram? Very unique. Okay, let's move on. So remember this formula? This is used for not mutually exclusive. Okay, and add the separate probabilities and then subtract anything that has been counted twice. That is the common outcomes. Okay, let's talk about in a normal pack of cards as another example. What is the probability, okay, of getting a king or a heart? For those of us that have not seen the normal pack of cards, I'm going to show you that right here. This is the normal pack of cards, guys. You can see that you have diamonds, you have hearts in the third row. Okay, in the second row you have the clubs. These are the clubs, and in the fourth row you have the spades. Okay, so diamonds, clubs, hearts, and spades. If you count each of them, they are 13 each. 13, 13, 13, 13. So if you add 13 plus 13 plus 13 plus 13 in 4 places, you're going to get 52. So the total number of cards in a normal pack of cards is 52. Okay, let's take a look at what the question is asking us to find. They're asking about getting a king and a heart. So you want to know how many kings do you have in the entire pack? Okay, now over here towards the end of each of the types of cards, for diamonds, you have the J here is called the jack, the Q here is called the queen, the K here is called the king, likewise for the others. Now you look at the first cards here for each of the types of cards, you see that the first one is A. It wasn't written as 1, it's A. So although it represents 1, but in a normal pack of cards, we don't call it 1. We call it ace, A-C-E. So this is ace, 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 ace. So this is ace of diamond, this is ace of club, this is ace of heart, and this is ace of spade. Same thing happens to these guys here. So the question was asking about king. So I have king of diamond, king of club, king of hearts, and king of club. I mean, king of spade, rather. So how many kings do we have in the entire pack? This is the entire pack. I can see we have 4 kings. 1, 2, 3, 4. There are 4 kings. How many hearts? I think they asked for hearts. Yes. How many hearts do we have? Well, all these cards here, all the 13 cards that we have here are all hearts, as you can see. So there are 13 hearts. Okay, so that simply means that the probability of king or heart is the probability of king plus the probability of heart. Now, guys, take note of this. Take note of this, guys. Look at this. Minus the probability of both. Why are we subtracting? We're subtracting because we realized that there is a king that is also a heart. Guys, this is it. Okay, there is a king that is also a heart, and that is the king of hearts. This card right here, this particular card right here. Okay, so please take note, guys. This is a common outcome. It is both a king and also a heart, and it's just only one card that is like that. So that simply means that we have to subtract. Okay, that's why we needed to subtract. Take note of that. So for over 52, remember we said there are only 4 kings and the total number of cards in the pack is 52. So that is 4 over 52. Number of hearts is 13. So probability is 13 over 52. And then there is only one outcome that is common to both king and heart. That means there is only one card that is both a king and heart. So that is 1 over 52 for its own probability. And when you proceed, you get 16 over 52. Very interesting. Moving on, guys. We have a number that is chosen at random from the whole numbers 1 to 50. Work out the probability that the number is, the first one, an odd number or a factor of 6. Let's do ourselves a favor. Let's do ourselves a favor by quickly putting out all the outcomes that we need to do this calculation. All right. So how do we do this? Let me do this. Let me just put it this way. An odd number from 1 to, okay, let me put it this way. Odd number from 1 to 50. So let me just say odd over here. Let me change the color. Odd over here is supposed to have the following, it's just 1, 3, I'm just going to say dot, dot, dot. Oh, okay, let me add 5, 5, then dot, dot, dot. It continues like that until I get to 49. Those are all the odd numbers, okay? All right. Then I'm going to have the other one, factor of 6. Factor of 6. And I'm going to have that to be equal to the following outcomes. I'm just listing out the outcomes. Factor of 6, I have 1, I have 2, I have 3, I have 6. 1, 2, 3, 6. Those are the factors of 6 that we have between 1 and 50. All right, taking a look at this, guys, what do you see? From 135 up to 49, I believe we're going to be having about 25 of them. Okay, so the probability of odd separately is actually 25 over 50. Okay, that's probability of odd. Let me just put it by the side. Probability of odd. I'm going to use O to represent odd. Let me use small letter O. Probability of odd is supposed to be equal to 25 over 50. Then we go for the next one, which is probability of factor of 6. So let me call that F6 so that we can just shorten things out. F6, factor of 6. Okay. Or let me just say F of 6. The probability for this is going to be equal to how many factors do I have? 1, 2, 3, 6. Just 4 of them. So that's going to be 4 over 50. That's going to be 4 over 50. Factors of 6. 4 over 50. So guys, we need to now take a look at the outcomes. What are we looking out for? Between the factors of 6 and the odd numbers, can you see any, okay, common outcome between these two outcomes? These are the outcomes for odd. These are the outcomes for factor of 6. Anyone common? Yes. We do have one that is common, and that is 1 and 1. Common outcomes. Okay. No, I have 3 as well, guys. So we need to look very well. So there are 2 outcomes that are common between these 2 events. So that simply means I must also talk about the probability of the common outcomes. So probability of, which I can write as explained before, odd intersection, let me use that as intersection, odd intersection factor of 6. So let me still call that F6, factor of 6. So the intersection there, which is the common outcome, probability of the common outcomes, is going to be equal to how many? We have 2 of it, so 2 over 50. That's what we're going to get there. So working this out, guys, the probability is going to be this plus this minus this. Okay, and 25 plus 4, okay, is 29, and 29 minus 2 is 27. So we expect the answer here to be 27 over 50. I'm sure you're following me, guys. I'm going to write it out. So what we expect this calculation is for the first one. What we expect is the probability. Okay, I'm going to write it under it so that I don't disturb the space for the other one. So we have the probability of odd number or factor of 6. I'm still going to maintain F6 for that to be equal to the probability of odd numbers plus probability of factor of 6 minus the probability of odd number intersection factor of 6. Okay. So we have to use this formula because the event is not mutually exclusive. So finally, we're going to get our answer to be equal to, so just do the addition, 25 over 50, okay, plus 4 over 50, then minus 2 over 50. I can quickly put that down and then we'll write the final answer there. So we have 25 over 50 plus 4 over 50 minus 2, okay, minus 2 over 50. And that will finally give us 27 over 50. So when you solve that for your 27 over 50, you can see that the format of our answer here, they expect us to have it in decimal. So we're going to take it to decimal. And when we take 27 over 50 to decimal, we simply get 0.54. So this is 0.54. Okay, moving on. I want you guys to do this now and quickly give me the answers. Okay, a square number or a factor of 15. So list out the outcomes of a square number, list out the outcomes of a factor of 15, find their probabilities, and also check if there's a common outcome or common outcomes, find the probability and apply the formula. Okay, let's go, guys. Start sending me your answers, okay? Send them in, send them in. Let me see what you have. Send in your answers quickly, 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 quickly. Quickly, 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 quickly. Send in your answers. I think you should get 0.22. And then for the last one, you should get 0.36. Okay, so if you're correct, okay, okay, okay. Let's do the calculations. I'm waiting for your answers. I'm waiting for your answers. I'm waiting for your answers, waiting for your answers. Okay, those answers were not the correct ones. Let's look for the correct answers. Please keep working, keep working, keep working. All right, keep working, guys. So if we have done with our calculations, let's find out. I think we should have the following answers, 0.2, and here we should have 0.46. Let's confirm this again and see what we have. All correct, well done. So I hope you know that if you are wondering what happened in the second one, please take note. When you are listing your outcomes for square numbers, 1 is also a square number, please take note. Most of us usually forget about 1 being a square number. A square number is just a number that is a perfect square, you know. 1 squared is 1, 2 squared is 4, 3 squared is 9. So you have 1, 4, 9, 16, 25, 36, 49 as your square numbers. Remember, we want them to be chosen from the whole numbers 1 to 50. So that's why I stopped at 49. And then the factors of 15, the factors of 15 is simply 1, 3, 5, 15. So you can fill in the rest. The outcomes for a multiple of 3 is just your multiple table of 3 up to before you get to 50, between 1 and 50. So if you do that, you have 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45, and 48. For a multiple of 5, you simply just have your 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. Okay, so that should help you to understand how we got these answers here. All right, moving on. Now, it can also be useful, guys, to visualize the OR rule on the Venn diagram. Very useful. Now you can see that a dice is rolled. Event B is getting an odd number and event D is getting a 6. The odd numbers that we have on the dice is 1, 3, 5. Okay, and that's 3 numbers. There's only 1 6, so that means 1, 3, 5, then 1, 6. There's nothing common. We don't have any common outcome between the two events. So the overlap has to be 0. And there are 3 odd numbers, so I put that for B. And there is only 1 6. I put that for D. Okay, let's take the total. The total number of possible outcomes should have been 6. So 3 plus 0 plus 1 is 4. So I should have 2 more remaining outside. And that is very correct. If you take a look at the next one, we'll see that, okay, there are no numbers that are both an odd number and a 6. That is why the overlap here is 0. The intersection is empty. So B and D are mutually exclusive. So since they are mutually exclusive and there's nothing common, we can simply separate the circles. And then we can see that using the OR rule for mutually exclusive events, probability of A or B is probability of A plus probability of B. If you check that out, you will see that this is 3 over 6 plus 1 over 6, because there are 3 required successful outcomes for B and 1 for D, so you have 4 over 6. Now, let's take another one. Another dice is rolled. Event E is getting an even number, and event F is getting a factor of 8. Okay, let's take a look at that. Even numbers on the dice, 2, 4, 6. Factor of 8, 1, 2, 4. You see, I've mentioned 2 numbers that are common now, which is 2 and 4. So that means this is 2. You can write out the outcomes and check the intersection. So I must have 1 more left to complete the 3 outcomes for even numbers, and 1 more left to complete the outcome of factor of 8. If I add them all together, I get 4. So I have just 2 more outcomes to complete the 6 total number of outcomes, and that is very correct. Let's take the next one, guys. E and F share the outcomes 2 and 4. That's the explanation there. So the intersection is not empty. E and F are not mutually exclusive. So the circles cannot be separated. So when you work that out, it must include minus the probability of the common outcomes. So you simply have probability of E plus probability of F minus probability of E and F. So 3 over 6 plus 3 over 6. Don't forget the total for E is 3, 1 plus 2, and the total for F is 3, 2 plus 1. That's why we have 3 over 6 plus 3 over 6, and then minus 2 over 6. Final answer is 4 over 6. Finally, let's take a look at the integers from 1 to 20. These are written on cards, and one number is selected at random. You want to pick a number at random. Find the probability that the number chosen is even. Okay, that will be 10 over 20, because between 1 and 20, there are 10 even numbers. Find the probability that it is a multiple of 3. That will be 6, definitely 6 over 20. Okay, because for a multiple of 3 between 1 and 20, you find out that you have only 6 of them, and that should simply be your 3, 6, 9, 12, 15, and 18. Only 6 of them. So the probability is 6 over 20. For both even and multiple, that is an intersection. That's a common outcome. So elements or outcomes that are both even and multiple of 3 between 1 and 20, you have the numbers 6, 12, and 18. That gives you the overlap, okay? So we have 3 over 20 for that, for the probability. Finally, D, probability that the number chosen is either even or a multiple of 6. Remember, I mentioned that that's another way of using the word or, either or. So it's going to be union, and the formula is going to be probability of E plus probability of M minus probability of E intersection M. We are using the minus one because this event is actually not mutually exclusive. So we have to put the subtraction there. So when we do that, yes. And then we're going to have 10 over 20 plus 6 over 20 minus 3 over 20 to give us 13 over 20. Now, guys, there are 13 numbers which are either even or multiples of 3, and they are 2, 3, 4, 6, 8, 9, 10, 12, 14, 15, 16, 18, and 20. Very interesting. Let's try to fill that into the Venn diagram right here. Okay, filling that in, you are going to have all these numbers They are even numbers. All these ones are multiples of 3, but the ones here in the middle are both even numbers and multiples of 3 at the same time. The ones outside here are none of both at all. So if you try to take a look at the total number of successful outcomes and total number of possible outcomes, we can take the totals, and this is 17 outside there, 3 in there, 3 in there, and then 7 in there. By the time you add them all together, you get 20. So we are very, very correct. Thank you very much, guys, for being attentive in today's class. I want to believe that this is very understandable. Now you have learned the difference between mutually exclusive events and not mutually exclusive events. And don't forget, we also talked about exhaustive events. And I believe all these are clear. Please, thank you very much for watching. Thank you for your time. I'll see you in my next video. Bye for now.